Hello and welcome back to this series on shapes. So I've had some comments underneath saying that people like the material I'm presenting, but can I improve the audio quality? So I've moved the microphone from on top of the camera to just down beside me, and we'll see if that works. If it doesn't, then next time I'll try a lapel mic. So we're talking today about quadrangles. So triangles, which we covered last week, have 3 internal angles. A quadrangle has 4 internal angles, and we'll come across multiple different types. So we'll come across squares, rectangles, parallelograms, rhombuses and trapeziums. So we'll start with the simplest of these, which is the square. And squares have some properties. So all 4 angles are the same and equal to 90 degrees. All 4 lengths have the same length, so we'll just call that A. It has 4 lines of symmetry, so going from the middle of the top to the middle of the bottom, the middle of the side to the middle of the other side, and across the diagonals. So we can fold a square equally 4 times, or in 4 different ways. And the area of the square is equal to the length times the height, which in this case will be A multiplied by A, or A squared. Next shape we have to consider is the rectangle. So rectangles are very similar to squares. They still have 4 equal internal angles of 90 degrees. Where they differ from the squares is that the height no longer equals the base. So we can call the base B and the height A. And they only have 2 lines of symmetry, which go from the middle of the top to the middle of the bottom, and the middle of the side to the middle of the other side. So there are no diagonal lines of symmetry on this. The area for the rectangle is the same as a square in principle. It's the base multiplied by the height, which is also, it just can be written as AB. So now let's imagine what happens when we have a rectangle that has been squashed slightly. So we have something that looks like this. This is called a parallelogram, and part of its characteristics is that it has 2 sets of parallel lines. So it has a set of parallel lines on the horizontal, and these ones that are almost going up towards the vertical are also parallel. So that's the same as with a rectangle or a square. However, with a parallelogram, you also have some internal angles which are different to 90 degrees. So in a parallelogram, opposite angles are the same. So I'll call these ones theta, and these acute angles alpha. So you have 2 obtuse angles, so they're greater than 90, and 2 acute angles which are less than 90, but all the angles will sum to be equal to 360 degrees. We can also have the length of the base. We can have the length of this more vertical side, which is A, but what we'll also have is a height. And the area of a parallelogram is equal to base times the height. And where this comes from is if I draw my parallelogram quite big here. So this is still my height, and this is my base. What I can do is I can take a triangle out of this, and I can move it to here. In which case this now just becomes a normal rectangle with height H and base B. So that's why this formula still works for parallelograms. A special case of parallelogram is the rhombus. So this is the equivalent of a squashed square. So In this case, the lengths of the sides are all the same, so there's still A. It will also have height of H. The acute angles are the same, they're still alpha, and the obtuse angles would still be theta. So we can use the same formula as the parallelogram to find the area of a rhombus, which would just be, in this case, A multiplied by H, which is equal to AH. There is another way of finding the area of a rhombus. So again, if I draw it out nice and large, if I draw my lines which link the corners, these don't have to be the same length, so let's call this one P and this one Q. If you notice, this will divide it into two equilateral triangles, and the areas of these equilateral triangles would be half the base. Well, let's make the Q line the base, so we're going to have half of Q multiplied by the height of each triangle, and half the height will be, in this case, half of P. And because we have two of them, we're going to add these two together, so we're going to have another half Q times a half P. So this is equal to the area. I'm going to change the black pen because it's going to make it a bit tidier or easier to see. So we've got a half times a half, which is a quarter. P times Q is PQ, plus another half times a half, which is a quarter, QP. So we have a half QP, quarter QP plus a quarter QP, which would equal a half QP. So if you know the lengths of these lines that link the corners, you can also find the area of your rhombus using this method. Finally, we have the trapezium. So the trapezium I need to make sure I draw this a bit better than that. So a trapezium has two parallel sides, one of length A, one of length B, and a height, which is H. These two other sides don't have to be equal. The angles still sum to be equal to 360 degrees, but they don't have to be, they're not in pairs, so they can be anything, so they can be alpha, beta, gamma, and theta. So the question is, what is the area of this shape? So the formula for the area is equal to half the sum of the parallel sides. The parallel sides are A and B, multiplied by the height, which is H. So if you can remember that, again, all well and good. And at GCSE, this formula is given in the formula booklet at the beginning of the exam. However, if you want to prove this, what we again have to do is draw it out nice and big. And with most of the techniques I'm going to be teaching in this series, it revolves around dividing it up into triangles. So if I take a triangle here and a triangle here, what we end up with is two triangles and a rectangle, and we need to add the areas of these triangles together. But what I can also do is take these two triangles and join them together. So if I take this triangle and this triangle, and I join those together, what I'd end up with is a triangle which would look something like this. It doesn't have to be a scalene triangle. If these angles are the same, then it will be. Sorry, it doesn't have to be an isosceles triangle. If these angles were the same, it would be an isosceles triangle, but this would actually be a scalene triangle. But what we can see here is the base of this triangle would be equal to b minus a, because this length here is a, therefore what's left over will be b minus a. And we still have the same height of these triangles, which would be h. So the area in this case would be the area of this rectangle, which is AB, plus a half b minus a multiplied by the height. So this is the area of this triangle, or these two triangles added together. Now what we have to try and do is see if we can modify this down so we get back to this general formula. So we can take this, first of all, let's look at, oh sorry, I've made a mistake here. This shouldn't be a times b, this should be a multiplied by h. So this is the height of that rectangle. So we have a times h. So we have ah plus, I'm going to expand this bracket out, so a half bh, so half times b times h, minus a half of ah. So I can bring like terms together, so ah minus a half ah is equal to a half ah plus that half bh, and now I can factorise this because we have a half and a h in both these terms. So I can take the half outside, the a will add to the b, and then we'll take the h over to the other side. So we've got back to this original formula. So that's how you calculate the areas of the different types of quadrangles. So in the next video we'll look at general polygons, so things like pentagons, octagons, hexagons, and just higher sides shape. So thank you for watching. Please hit that subscribe button so you can keep up to date, and if you hit the notifications icon you'll get a notification so whenever I release the video, and the notifications icon is the bell. Anyway, see you again soon.